You see it every single day, without even thinking about it. The way your coffee swirls in the cup, the way your phone stays firmly in your hand, the way light fills your room the moment you flip a switch. It all feels predictable, controlled, understood. But here's the terrifying truth. Some of the most basic things in your life are powered by laws of physics that we don't actually understand. Not partially, not approximately, completely. In fact, the deeper scientists dig into reality, the more they uncover something disturbing. The universe isn't just mysterious, it might be fundamentally broken. These are 10 physics problems that no one on Earth can solve, and the deeper you go, the more it feels like reality itself is hiding something from us.
Number 10. The turbulence mystery. You've seen it your entire life, but you've never really thought about it. When you pour milk into coffee and watch it swirl into chaos, when smoke rises from a fire and suddenly breaks into wild, unpredictable patterns, or when you're sitting inside a plane and it suddenly drops for a split second for no reason you can see, that's turbulence. It looks simple, even beautiful, but behind that beauty is one of the deepest unsolved problems in all of physics. Because here's the shocking truth. We use equations to predict fluid motion every single day. They help design airplanes, cars, ships, even weather systems. But when things get chaotic enough, those same equations start to behave like they are breaking reality itself. In extreme conditions, the math can produce results that explode into infinity, as if nature refuses to follow its own rules. And the terrifying part? We still don't know if the equations that describe all of fluid motion actually always work. Somewhere inside something as ordinary as water or air may be a hidden chaos so complex that even the most advanced physics on Earth cannot fully control it.
Number 9. The weakest force paradox. Take a moment and look around you. Everything you see, your phone, the table, your own body, is held together by invisible forces you never notice. Now pick up a simple object, like a small iron nail. Place it on a table. Then bring a tiny refrigerator magnet close to it. In an instant, that nail moves. It jumps. It follows the magnet like it's being pulled by an invisible hand. Now here's where things get strange. At that exact same moment, the entire Earth is pulling that same nail downward with its full gravitational force. Not just the Earth, the entire mass of the planet, 6 septillion kilograms of matter, constantly dragging it toward the ground. And yet, a tiny piece of magnetized metal easily wins. That shouldn't feel normal. Because gravity is supposed to be one of the fundamental forces of the universe, the force that shapes planets, stars, and galaxies. But compared to electromagnetism, it is unbelievably weak. So weak that the difference is almost incomprehensible. A gap so massive it stretches to numbers like 10 to the 36th. And that raises a disturbing question. Why is gravity so powerless? Even stranger, if gravity were just slightly stronger, stars would burn out too fast for life to exist. If it were slightly weaker, galaxies might never form at all. It feels like gravity is not just weak, but perfectly adjusted. Some theories suggest something even more unsettling. Maybe gravity isn't weak at all. Maybe it's leaking into hidden dimensions we cannot see, spreading itself across realities beyond our perception. What we experience might just be a faint echo of a much stronger force hidden somewhere deeper in the universe. Number 8. The theory war. Modern physics rests on two of the greatest achievements in human history. On one side, Einstein's general relativity, the theory of the massive, the cosmic,
the enormous. It explains how planets move, how stars collapse, how galaxies bend space and time itself. It is smooth, elegant, predictable. Now go to the opposite extreme, quantum mechanics, the physics of the unbelievably small. Here, nothing behaves normally. Particles don't sit still in one place. They exist as probabilities. They appear, disappear, and behave like reality itself is guessing. And here is the terrifying problem. Both theories are correct. We've tested them, repeated them, built our world on them. But they refuse to work together. The moment you try to combine them into a single equation, the math collapses. It doesn't just get difficult, it breaks. It produces infinities. It produces nonsense. As if the universe is saying, "Wrong system, try again." This becomes a real problem in places where both extremes exist together. Inside black holes, or at the very beginning of the Big Bang, where the universe is both infinitely large in power and infinitely small in scale. In those moments, neither theory is enough, and we are left with a disturbing truth. We don't have a complete description of reality. Somewhere deep inside the universe, there must be a single hidden rule that connects everything. But right now, it is completely out of reach.
Number 7. The perfect symmetry problem. Deep inside every atom in your body, there is a hidden world of forces holding everything together. At that scale, physics has a rule, a kind of mirror test. If you take a particle and swap it with its antimatter version, and then flip it like a reflection in a mirror, the laws of physics should behave exactly the same. This idea is called symmetry. And for one of the fundamental forces of nature, the strong nuclear force, this symmetry should matter a lot. Because the math of particle physics actually allows it to break this rule. It should create a tiny imbalance inside matter, a small distortion in how particles behave. But when scientists look, they find something shocking. Nothing. No imbalance, no distortion, no signal of violation at all. It is as if nature is perfectly fine-tuned to stay symmetrical with impossible precision. Experiments have measured this effect down to extreme accuracy, and still the universe refuses to show even the smallest flaw. That raises a disturbing question. Why is the strong force so perfectly balanced when the math says it shouldn't be? To explain this, scientists proposed something new, a hypothetical particle called the axion, a kind of invisible cosmic fix that would naturally correct this imbalance. But there's a problem. After decades of searching, underground detectors, high-energy experiments, cosmic observations, we still haven't found it. So the symmetry remains perfect, too perfect. And in physics, perfection without explanation is never comforting, because it usually means something is missing from the picture.
Number 6. The missing monopoles. Take a simple bar magnet and hold it in your hand. You'll notice something strange about it, even if you never thought about it before. It always has two ends, a north pole and a south pole. Now cut it in half. You might expect to isolate one pole, a single north or a single south, but that's not what happens. Instead, you just get two smaller magnets, each with its own north and south again. No matter how many times you cut it, the rule never changes. Magnets always come in pairs. But here's where physics becomes unsettling. According to many fundamental theories, especially those describing the early universe, this shouldn't be guaranteed. In fact, in the extreme conditions of the Big Bang, nature should have created something far stranger, a magnetic monopole, a particle with only one magnetic pole, either north or south, existing alone in space, not paired, not balanced, just single. And the math doesn't just allow it, it demands it. Even one monopole somewhere in the universe could explain deep mysteries about how electric charge works. But despite decades of searching, in cosmic rays, in ancient rocks, in particle accelerators smashing matter at insane energies, we have never found a single confirmed example, not one. Which leads to a disturbing possibility. Either the universe once created these objects and we simply haven't found them yet, or something happened early in cosmic history that erased them almost completely. One popular idea is cosmic inflation, a violent expansion of the universe that could have stretched and diluted them beyond detection. But that raises a deeper question. If the equations say they must exist, why can't we find even one?
Number 5. The ghost particle mystery. Right now, as you're watching this, you are being passed through by something invisible. Not once, not twice, but trillions upon trillions of times, every single second. These are neutrinos, ghost-like particles born in the heart of stars, in cosmic explosions, and even in radioactive decay all around us. They move straight through matter like it isn't even there. Your body, the Earth, entire planets. To a neutrino, it's all basically empty space. For a long time, physics had a simple rule for them. Neutrinos were supposed to have no mass at all, pure energy moving at the speed of light, untouchable and eternal. But then, something unexpected happened. In 1998, scientists studying neutrinos coming from the sun noticed something impossible. They were changing. One type of neutrino was turning into another as it traveled through space, like it was shape-shifting on its journey to Earth. And that created a contradiction, because for a particle to change like that, time must pass. And if time passes, it cannot be moving at the speed of light. And if it's not moving at light speed, it must have mass. That discovery shocked the physics world. It even won a Nobel Prize. But it also shattered a core assumption of the Standard Model. Because now we know neutrinos do have mass, but it is so unbelievably small that we still cannot properly measure it. And worse, we don't know where that mass comes from. The Higgs mechanism explains most particles, but not neutrinos. So they point to something deeper, something hidden, a layer of physics we have never seen, quietly influencing the universe from beneath everything we understand. Number 4. The missing lithium. Let's go back to the very beginning of everything. Not Earth, not the solar system, but the first few minutes after the Big Bang. At that moment, the universe was nothing like it is today. It was a rapidly expanding, ultra-hot furnace of pure energy where the first atoms were just beginning to form. Hydrogen, helium, and one more element, lithium. Using the laws of nuclear physics, scientists can actually calculate how much of each element should have been created in that early cosmic fire. And when we test that prediction against reality, something incredible happens. For hydrogen, the match is perfect. For helium, again, perfect. But then we look at lithium, and everything breaks. Because there is a massive gap between prediction and observation. The universe should have produced a specific amount of lithium-7 in its first few minutes. But when we observe the oldest stars in existence, we find only about 1/3 of what should be there. 2/3 is missing, gone. Not slightly off, not a small error, a cosmic-scale accounting failure. And no one knows why. Did something destroy lithium in the early universe? Did unknown particles interfere with its formation?
Or is there a process inside stars that slowly eats it over billions of years? Every explanation creates more questions than answers, because this isn't just about one missing element. It's about whether our entire model of the universe's birth is incomplete. If we can miscalculate something this fundamental, what else are we wrong about?
Number 3. The death of matter. Everything in the universe has an ending. Mountains collapse into dust. Stars burn out and fade into darkness. Even galaxies slowly drift apart until nothing meaningful remains. But there is one question physics cannot fully answer. Does matter itself die? At the center of everything you see around you are protons, the building blocks of atoms. They make up your body, the air, the ground, everything. And according to the standard model of physics, protons are supposed to be stable, forever stable, meaning matter should never truly decay. But here's where things get unsettling. Many advanced theories that try to unify physics predict the opposite. They suggest that protons should eventually decay into lighter particles, slowly breaking down over unimaginable periods of time. If that is true, then matter is not permanent. It has an expiration date, and the universe itself is slowly heading toward a silent end where everything dissolves into radiation. To test this, scientists built massive underground detectors filled with thousands of turns of ultra-pure water, waiting in total darkness, watching for a single proton to die. Years passed, decades passed, and nothing happened. Not one confirmed decay. This means that if protons do decay, their lifetime must be at least 10 to the 34th years, far longer than the current age of the universe. So now, physics is stuck with a terrifying uncertainty. Either matter is truly immortal, or we are simply living in a universe that hasn't waited long enough to reveal its decay. And somewhere in the equations of reality, there may be an eventual ending written into every atom that has ever existed.
Number 2. The observer effect horror. This is where physics stops feeling like science and starts feeling like something else entirely. In the quantum world, nothing behaves the way your intuition expects. An electron, for example, doesn't sit in one fixed location like a tiny planet orbiting a nucleus. Instead, it exists as a cloud of probabilities, a blur of possibilities. It is, in a very real mathematical sense, everywhere and nowhere at the same time. And this isn't just theory. It's been proven in one of the most famous experiments in physics, the double-slit experiment. When electrons are fired at a barrier with two slits and nobody is watching them, they behave like waves. They pass through both slits at once, interfering with themselves, creating a pattern that only waves can produce. But the moment you try to observe them, the moment you place a detector to see which slit they go through, everything changes. The wave disappears. The electron behaves like a single particle, choosing one path as if it suddenly knows it is being watched. Just the act of measurement changes the outcome. And here is where things become deeply disturbing. Because physics still cannot explain why this happens. How does a particle decide to behave differently when observed? What counts as an observation? Is it a machine, or is it consciousness itself? Some interpretations suggest something even stranger, that every possible outcome happens but in separate branching realities. Others suggest that reality doesn't fully exist until it is measured. That without observation, the universe is not a solid thing, but a shifting cloud of probabilities. and the act of looking is what forces reality to choose. It turns physics into something unsettlingly personal because it raises a terrifying question. If nothing is observed, does it even exist in a definite form at all?
Number 1. The Fine-Tuning Nightmare. Grand Finale. At the deepest level of reality, there is no random chaos guiding the universe. Instead, physics reveals something far more unsettling. It reveals a kind of hidden control panel, a set of around 20 to 30 fundamental constants that define everything that can ever exist. The mass of particles, the strength of gravity, the speed of light, the energy of empty space itself. These are not explained by any deeper theory we currently know. They are simply given. And here is the terrifying part. If you adjust even one of these values by an almost invisible amount, the universe collapses into something unrecognizable. If the strong nuclear force were slightly stronger, atoms wouldn't form properly. If gravity were slightly weaker, stars and galaxies might never come together. If dark energy were even a fraction different, the universe would have expanded too fast for any structure to exist at all. It is as if reality is balanced on a razor-thin edge between existence and nothingness, a precision so extreme it defies intuition. The odds of all these constants aligning perfectly for life appear so small that they feel almost impossible. Yet here we are. This raises a question that physics cannot avoid. Why is the universe calibrated this way? Some scientists suggest it is pure chance, an accidental outcome of a single universe among many, a multiverse where every possible combination of laws exists, and we simply happen to live in the one that allows observers like us. Others take it further, suggesting that reality might not be accidental at all, that these constants could be the result of design, selection, or a deeper structure we do not yet understand. But at the end of it all, there is no confirmed answer, only silence, and a universe that appears to be balanced with impossible precision, as if it was tuned for something.